Okay. Okay, so this good to be here. It's a very interesting set of talks. I was afraid there would be a lot of overlap, but so far it's different angles to similar topics. So it's been very interesting so far. So I'll try to add a little bit to this. So I am Willem Jan Palenstijn. I am the lead author of the ASTRA-toolbox. I'll introduce Astra a little bit, talk about our Python integration over the years, the current state of our PyTorch integration, and then a little bit about ongoing plans for the near future if there's time. I need to look on the right place. This is very interesting. Oh, okay, my laptop does not like this. Yeah. Anyway, so Astra, it's basically a set of fast and flexible building blocks for 2D and 3D tomographic reconstruction. So mainly a forward and back projection operator. It's written in C++ and CUDA behind the scenes. It has MATLAB and Python interfaces. It has support for many geometries, and it is entirely free and open source. We started this, I say we, I was entirely involved at the beginning. It was started in 2007. I joined myself in 2009, I think it was. It started at the University of Antwerp, at the Vision Lab, a bunch of PhD students that were starting at the same time. Were starting on tomography projects and decided to kind of build this library from scratch using CUDA, which was just starting. So we were starting our CUDA 3, I think, a long time ago. It grew. There was external interest at some point, so from synchrotrons, from FEI, and electron microscopes. We had our first open source release in 2012. In 2014, some of us moved to CWI in Amsterdam in the Netherlands, and so then it's a joint project. And it's, at the top, there's also University in Leiden. That's where I'm working now since the past 2 years, so it's now kind of a 3-institute project. We're still actively developing. We had a 2.0 release in 2019, a 2.3 release in February, I think it was, maybe March. Oh, March, I think. No, pretty recent. And we're gearing up for a new release in the summer. We support 2D parallel beam, time beam geometries, 3D parallel cone beam geometries, and a very, very new feature that we just merged is support for cylindrical detectors. So this is mainly for the medical world. All of these is flexible source detector positioning. So basically in Euclidean space, you position where your source and detector are. We have a few basic reconstruction algorithms, but mainly how it's used effectively by many people here is as a forward and back projection, providing toolbox. What we do not provide is also important to mention to set expectations. We do not do any data I/O stuff, so we can't read files produced by scanners or synchrotrons. We don't do any data alignment, pre-processing, filtering for artifacts, and we don't have any modern advanced reconstruction algorithms. We kind of decided to stick to the projection operators and let other groups handle the reconstruction algorithm development.
You mean by modern?
That is an excellent question. Basically anything after, say, CTLS. Yeah, and not even the fancier linear solvers. So our architecture, so there are many layers. There's the hardware. On top of that, we use CUDA to address the NVIDIA GPUs. There's a main C++ layer. We started with the MATLAB interface, actually. Python grew much more popular. So probably Python should crowd out the MATLAB box a bit by now. So most of the usage of Astra is probably nowadays through the bigger Python and PyTorch ecosystem. So just a few concepts, if I accidentally use some of these words in the rest of the talk. So how we define geometries in Astra is you put a projection geometry and a volume geometry together in an object with a low projector, and then you give this projector together with volume data and projection data to an algorithm, which can be a forward projector, back projector, or a SERT or FPP or FTK algorithm, and then it will run this usually on the GPU. So We have Python integration. At some point, Dan Pelt from CWI was at the time at CWI, a PhD student there, decided Python is becoming more popular. We need a Python interface, so we just wrote this, and it was very closely modeled on the C++ interface. We use Cython to do the interfacing. So Cython is basically, it's a language that is mostly Python, but it is compiled to C and is very convenient for accessing C stuff from a more Python-like language. So it's kind of in the middle between C++ or C and C++ and Python, and so it's a very nice bridge between the two. You can, if you want, you can use Cython to write C++ classes, and if you want, you can use Cython to write Python classes and access them from both. Our interface is not very Pythonic, but we use handles, which are effectively integers to kind of access or to refer to instances of our C++ objects that are allocated and managed behind the scenes. So the very low level way of doing this, you create a data object, which is basically a large float 32 buffer behind the scenes. It's allocated this array in the C++ interface. It gives this ID, which is an integer, back for future reference in Python. It's storage for volume data, so it's either be a phantom or reconstruction or projection data. It is tied to a geometry, so we make the same decision that objects, they are tied to metadata. So the Astra C++ object that comes with a pointer to a geometry. And these objects are used with the Astra algorithms and forward and back projection code. So this was the very, very first way of managing memory from Python. And if you want to then use this, and this is roughly what it looks like, you define a geometry. I won't spend too much time on this. You create some geometries, you create data objects, you create an algorithm with these data objects, and you run it, say in this case, circ for 100 iterations. And at the end, you get the data back from this allocated C++ memory object to a NumPy array for future use or visualization in Python. The next step forward was link. So that basically uses Cython and NumPy functionality to share memory between NumPy arrays and C++. So on the C++ side, we basically have a storage class that points into NumPy, which saves a lot of memory. It saves copying and makes life much better. It's still used in the same way. You just have an ID that you can use with the same in the same way. Next step up is what we call Optomo. This makes it a little bit more Pythonic. So you have this projector that combines a projection geometry and volume geometry, and you create this projector. You use create projectable, and you give this to an Optomo object, and this is the W here, and that's kind of now a more Python-like object. So this inherits from SciPy linear operator. It has some convenience functions like reconstruct, and you can give this a NumPy array that internally then uses the link functionality, etc. And for instance, because it's a linear operator from SciPy, you can also use for instance, SciPy's LSQR and various other algorithms. So things got a little bit more convenient by now. This is also the time that more and more packages start popping up that use Astra as a backend. And to kind of facilitate that a bit, we added a interface that kind of bypasses more of the object management, which we call the direct FP-BP interface. So you still create a projector, which has the geometries. And now, so behind the scene, there's a C++ object that has these parsed versions of the geometries, which are on the Python side, system dictionaries with the right values. And now there is a call to direct FP-BP, or FP3D or BP3D. It's in an experimental module, but it's pretty stable by now. We should at some point make a release where you move this to a more natural sounding place. You give this projector, and then you just give it a volume data and a projection data object, and these are pre-allocated NumPy arrays originally. So one of them is the data, the other one is basically the storage, and that gets filled with the data. So this is a pretty low overhead way of calling Astra on CPU data at the time. Then we are really going through history here. So more GPU toolboxes started popping up, and so we kind of wanted to bypass the CPU-GPU copying. And so we added a featured GPU link. This is very ugly. Basically, you give it a raw CUDA pointer as an integer, together with the dimensions. You give this to the Astra data to the link function that was previously used only for NumPy arrays. And now suddenly you can use this to give GPU memory to Astra. So actually using it takes a bit of low-level stuff, but for instance, you can now, using this functionality, you can take from a PyTorch CUDA tensor, you can take the raw pointer, give that to Astra, and then use Astra directly in Torch tensors. And so this is done by a library called Tomosipo. So this was developed by Allard Hendriksen, who was a PhD student at CWI at the time. I think he works at NVIDIA now. I don't think he's left there yet. So he moved there after graduating. It's now maintained by Dirk Schut and Alex Kotikov at CWI. Alex is probably in the audience online at the moment. And this is a much more Pythonic, user-friendly wrapper around Astra, and specifically it provides easy integration with PyTorch. And then I'll show a little bit more about the details. But in a high level, so it is a Python library. It supports CPU and GPU tensors. It uses Astra's GPU link functionality to access these tensors directly from the GPU. It computes and propagates gradients via the back projection operator. And it can also handle batch and channel dimensions in PyTorch tensors, which is a very common case, common use in the deep learning world. So then the latest functionality in Python integration is the LPAC support. So the LPAC has been kindly introduced already. It is, to quote, an open in-memory tensor structure for sharing tensors among frameworks. And it is supported by anything basically we wanted to use. The 1.0 release is pretty recent, so like half a year ago, where they added versioning to their structure, so it should now actually be future-proof. And it supports both host memory and GPU memory tensors. So the nice thing now is that since Astra 2.3, so since a few months, you can just give any tensor either CUDA or host memory that's from a framework that supports the LPAC to Astra using the link function and also to the direct FP3D or BP3D function. So putting this together, so Alex prepared a notebook, and I hope I shared my full screen, so this is now also visible online. So how to put this all together?
Can you make it larger?
I don't know. Yes, thank you.
Thank you.
To basically put it all together. So this X-ray operator here is basically a quick function or a quick class that calls Astra. So you can see for the output data, it uses Torch zeros to allocate output memory. Oh, wait, why is this so much larger on my screen than interesting? Oh, well. It allocates output data using Torch zeros. It calls the direct FP3D using the input data and the output data. And so basically with a few lines of code, you can call Astra directly on a CUDA tensor. And then I'll scroll down a little bit. So you can use this and you can use it to reconstruct, and you can hook it up to the autograd engine. So this has also been shown already. So you inherit from Torch autograd function, you define a forward and a backward, and then basically you are done, and you can use this from Torch. And then you can, for instance, do a reconstruction the PyTorch way by giving it a cost function and calling Adam in this case to optimize it, and you get a reconstruction out of it. Right, so I can share this demonstrator if that Alex wrote if people are interested. And then I briefly wanted to show some other pieces of code that hook into other things that have been mentioned. Wait, that is not what I wanted. So yeah, so one interesting thing, the LPAC. So it's sorry.
Make it larger.
Yes, with your image. So the LPAC. So we access it from C++. So and basically there's a large switch on the device type. So we decide if you get a CPU, one of type CPU or a CUDA host pointer, then we create a data storage the LPAC CPU class object behind the scenes. If you get a CUDA or a CUDA managed type, then give it a GPU thing. So I was just looking it up to see if we actually supported CUDA managed memory, and apparently we do. I haven't actually tested this. I'm very curious how this behaves. For our temporary memory, we do use CUDA malloc array, using the, as you noticed, very brilliantly named CUDA array. And so I'm very curious how it will behave and how it will, what the timing will be like comparing the two. So that was one thing I wanted to quickly see how we did that, and apparently we do that. And the other thing is a pretty new thing, and so Alex is probably the person to talk more about this. So if there are questions about this, I'll refer you to him. So there is now. So the AutoGrad system has been extended a little bit with something that used to be called functorch, and it's now imported into Torch as Torch Func. And it's more like a function composition thing inspired by JAX. And I can add a few more functions to. You can add a few more functions to your class. One of them is JVP, the Jacobian vector product, which has been mentioned. The other one is VMap, which kind of maps something over additional dimensions, which kind of makes it hook in a little bit nicer to this torch.func framework. Okay, so I wanted to show a little bit of code. If there are any questions about this, I will be happy to answer them now or anytime later. And to wrap this up, a brief thing about the things we are working on at the moment. So they are plans that are being executed at the moment. So one of them is a very interesting one, at least to me, which is AMD support. So NVIDIA is kind of behaving like a monopoly lately, so we were like, maybe we should look at other platforms. And I was really pleasantly surprised by the HIP platform that AMD has now. Basically, they have a function Perl script called hipify. It replaces CUDA malloc by hip malloc. It replaces CUDA free by hip free. It replaces, no, you can get the picture. And basically, it just works, at least with the subset of CUDA functions we call. So it was literally like I sat down and 2 hours later, I had a working Astra on a AMD machine, of which an hour was basically kicking our build system into accepting HIP-CC instead of MVCC, and I'm not being too scared about that. So that was really, I was really pleasantly surprised. So the LPAC also supports Wacom tensors, we still need to hook that up, and this is something we hope to have available in the near future and start testing and see where it goes. We're working a little bit on battery memory management, so especially in corner cases where like some input is GPU, some input is host memory, and how we allocate them pretty good first. We're not really optimizing it, and sometimes if you use the wrong combination, we'll allocate memory that isn't there, and so that will be better in the release in the summer. We're thinking about if we want to do batch dimensions in Astra itself, so that we can do some better parallelization, especially for 2D, for stacks of 2D things, which in the deep learning world is pretty interesting, and so basically giving Astra a stack of 2D things, we can do that faster than doing a loop in Python. Different data types, also very deep learning inspired. So we have some work on templating our backend so that it can also support 16-bit input, for instance. Also, we still want to accumulate into 32-bit. And we are looking at hooking up Kernel Tuner, which is a project by Ben van Werkhoven mainly. It started. He's now in Leiden. Also, he started this project at the Netherlands eScience Center, which is a group of research software engineers, to optimize kernel parameters for specific hardware geometry. So basically, you say these are parameters which are tunable. So like the number of threads in a block, the number of slices that each kernel executes at once, some other parameters. And then it's basically has a bunch of optimization algorithms that recompiles the code with these other parameters, tries how fast the code is, if it actually is correct, if it still gives the same output, and then either does a brute force or some other fancy search algorithm to find a better way. And especially if we also want to start supporting AMD hardware, so this is kind of the hook that we want to kind of see how if we should do this very different, the kernel configuration. So that was the last slide. Thank you for your attention.